Latimer diagrams. In the previous class, we have discussed about the variable oxidation states of D block elements. In this class, you will be studying how to find out the stability of various oxidation states. So, in order to understand the stability of various oxidation states, we should have a simple graphical representation, that is nothing but Latimer diagram. In this diagram, you will be having a Latimer diagram. You will be having a data of redox potentials, data for various off-cell reactions corresponding to different oxidation states of an element. Suppose is show exhibiting +2 oxidation state, +3 oxidation state, +6 oxidation state. We need to understand the stability of these different oxidation state. In this graphical representation, you will be having a redox potential data for each individual oxidation states. These are represented, that is known as Latimer diagram. Let us consider an element M which is showing different oxidation states like +4, +3, +2, +1, 0, like this. Element M is showing different oxidation states. These are connected by an horizontal line. These oxidation states of this element are connected by an horizontal arrow, like this. Horizontal arrow. You may observe that I have written these oxidation states in the decreasing order. So you can see +4, +3, +2. So highest oxidation state should be written on the left side and lowest oxidation state should be written on the right side in this diagram. So various oxidation states are written in the decreasing order of their oxidation state. Highest oxidation should be on the left side and lowest should be on the right side. Potential or standard reduction potential for the conversion of M+4 to M+3 is written here on the horizontal line. Let it be E0 of first step, that is E0 1. For the second step, there will be a corresponding E0 value that should be written on the horizontal line here, that is E0 of 2. So E0 value for the third step, that is conversion of +2 oxidations to +1 oxidation, is written here, which is corresponding to third step, like this. Suppose conversion of M+1 to M0 oxidation is written here as E0 of 4. Suppose if you want to find out the reduction potential for the conversion of M+3 ion to M+1 ion can be written here, that is E0 value of this corresponding value, that is E0 5. Like this, you have to write the Latimer diagram. So E0 values should be written. What is meant by E0 value? That is standard reduction potential value. So which is a measure of the tendency of a chemical species to get or to acquire electrons to get reduced is given by, which is compared with standard hydrogen electrode whose E0 value, that is redox potential, is 0. E0 value of hydrogen electrode is a 0. We will compare these chemical species with the standard hydrogen electrode. That is written here. E0 value for a chemical species which is highly positive. Highly positive indicates that the chemical species has greater affinity for electron, so that it is easily reduced. easily reduced. So, and which is a good oxidizing agent, which behaves as a chemical species which has high positive charge, has greater affinity, which can be reduced easily and acts as a good oxidizing agent. Suppose the E naught value, that is standard reduction potential values, negative, that is highly negative value, indicates that there is a lesser affinity for the electrons, so it won't accept electron, it can lose electron, so it can be oxidized easily. That means it acting as a good reducing agent. Understood? In this diagram, we have omitted many species like H plus ion, OH minus ion, number of electrons, and water molecules are omitted to simplify the diagram. In this reaction, to convert M plus 4 to M plus 3, suppose M plus 4 has to be converted to M plus 3, M plus 4 has to accept one electron from the from other species to get reduced. So this electron has been omitted to simplify this. So species like H plus ions, OH minus ions, number of electrons, some water molecules are omitted in this diagram. This is how the Latimer diagram looks. We can study the pH variation by using Latimer diagram, so that we can write the Latimer diagrams at pH 0, that means in acidic medium, and also at pH 14, that means in basic medium. So we can study the effect of pH on the redox reactions can be studied by using effect of pH can be studied by using Latimer diagrams. This is the one of the application of Latimer diagrams. So what are the information that we get from the Latimer diagram then? The first information after seeing the Latimer diagram that we get is, which is the good oxidizing agent and an reducing agent can be identified by using this Latimer diagram. The second application is the thermodynamic stability. Thermodynamic stability can be studied because we have a relation between E naught and delta G naught. Delta G naught means standard change in free energy. So we have a relation between E naught and delta G naught, that is delta G naught is equal to minus N of E naught, where N is nothing but number of electrons involved in the redox reaction, and where F is nothing but Faraday's constant, which is equal to 96,500 coulomb per mole. And E naught, as we know, the standard reduction potential value. By using this, we can calculate or we can find out the thermodynamic stability of a metal ions or elements. The third application of this Latimer diagram is we can study the disproportion reactions. What is meant by disproportion reactions? Suppose if you consider a galvanic cell where zinc is oxidized to zinc plus 2 ions by losing 2 electrons, which is a good reducing agent in the galvanic cell. And In the galvanic cell only, copper plus 2 ions which are in the solution will accept 2 electrons from the zinc and will become copper, which is deposited on the copper electrode. Here the copper is acting as a good oxidizing agent, is it not? Which is accepting electron, which is a good oxidizing agent. So in this reaction, in this overall reaction, one is getting, if you write the overall reaction, zinc plus copper plus 2 is undergoing, is in equilibrium with zinc plus 2 ions and copper. In this reaction, one is undergoing oxidation, another is undergoing reduction. So such reaction, in the redox reaction, it is usually like this. But some of the species can take metal ion, M plus ion, which undergoes self oxidation and also self reduction, which undergoes self oxidation to self oxidized to higher oxidation state, and which is reduced to the lower oxidation state. That means a single species is undergoing both oxidation and which is undergoing both reduction. So which is the oxidized product, which is oxidized, and which is M is reduced. Here the metal ion is in the solid state, reduced. Like this, such reactions where a single species undergoing both oxidation and reduction, such reactions are called as disproportion reactions, using the Latimer diagram. And the fourth application is feasibility of the reaction. That means whether the reaction is spontaneous or non-spontaneous can be identified by using these Latimer diagrams. What are the four different applications of Latimer diagram? First one is we can identify the oxidizing agent and the reducing agent. We can identify the thermodynamic stability, and we can study the disproportion reaction, and the feasibility of a reaction be studied by using Latimer diagrams. With this, we will write the Latimer diagram for iron. So, in order to write the Latimer diagram, we should have a off reaction. The first off reaction of iron is iron plus 2 can accept 2 electrons and get converted into iron, which is in the solid state. Standard reduction potential for this off reaction is equal to minus 0.44 volt. The second off reaction is the iron plus 3 ion can accept 3 electrons and get converted into iron. Is all these are reduction reaction. That's why we are writing E naught values. That means standard reduction potential values. The standard reduction potential value for this step is minus 0.057 volt. The third off reaction is iron plus 3 can accept 1 electron and to become iron plus 2. The standard reduction potential for this step is plus 0.77 volt. The fourth reaction here, FeO4 minus 2, that means this is a ferrite ion which can accept 3 electrons to become iron plus 3 by accepting 3 electrons, which is reduced to Fe plus 3 ion. Here, in order to balance this equation, here we have 4 oxygen atoms. That's why we will be adding 4 water molecules, and here you will be having 8 hydrogen. That's why you will be adding here 8 H plus ions. This is the balanced equation. For this step, the standard reduction potential value will be plus 2.2 volt. So you can observe here the iron can show plus 2 oxidation state is existing in plus 2 oxidation state, plus 3 oxidation state, and plus and 0 oxidation state. Here you can observe iron is in the plus 6 oxidation states. These are the 4 different oxidation states of iron. So to write the Latimer diagram for this of reactions, first you need to identify the highest oxidation state, that is iron plus 6, which should be written on the left side. Here the iron is in plus 6 oxidation state. Highest oxidation state should be written on the left side. So next higher oxidation state is Fe plus 3. The next higher one is plus 2. The next one is iron 0, which is in the solid state. These are the 4 different steps of. Here you can observe first half reaction is Fe plus 2 to iron, which is correct, we have written, and Fe plus 3 to iron we haven't written. Here we have to represent non-adjacent species. Reduction values of non-adjacent species can also be written in this Latimer diagrams. This is the lowest oxidation state of this iron, which is written on the right side of the Latimer diagram. Reduction potential values in the Latimer diagram. For the conversion of Fe plus 6 to plus 3, what is the value of E naught? Plus 2.2. That should be written on this arrow, 2.2 volt. The next of reaction is Fe plus 3 to Fe plus 2. This one. For that, E naught value is plus 0.77 volt. The next half reaction is Fe plus 2 to 0. For this, minus 0.44 volt. And the next reaction is, which is non-adjacent species, Fe plus 3 to 0. For that, we have a standard reduction potential value minus 0.057 volt. This is the Latimer diagram for iron. Now, what are the information that we are getting from this Latimer diagram of iron? First information is E naught values. By using this E naught values, you can tell that which is the good oxidizing agent and which is the good reducing agent. Higher the value of E naught, then that will be the good oxidizing agent. Which is the highest E naught value? Here it is. Therefore, FeO4 minus 2, that is ferrate ion, is a good oxidizing agent. The next one is higher negative value of E naught value indicates that can be a good reducing agent. Next one is the thermodynamic stability. To find this, we have a relation, that is delta G naught is equal to minus N of E naught. We need to calculate the delta G naught value for each step. Then only we will get the thermodynamic stability of these species. For the first step, which is Fe plus 6, here it is. Fe plus 6 is getting converted into Fe plus 3. For this, we have a E naught value of plus 2.22 volt. So that if you calculate delta G naught value, how many electrons are involved in this reaction? 3 electrons. That's why minus 3 into F, Faraday's constant, into what is the E naught value? Plus 2.2 volt. After calculating this, you will get minus 6.6 F is the delta G naught value. Similarly, for the second step, that is Fe plus 3 ions is getting converted into Fe plus 2. So, for this reaction, E naught value is plus 0.77 volt. Delta G naught value will be equal to, standard change in Gibbs free energy will be equal to, how many electrons are involved in this reaction? Only one electron, minus 1 into F into, what is the E naught value? Plus 0.77 volt. So that you will get minus 0.77 F, that is Faraday's constant. And the third step is, you can observe here, iron plus 2 is getting converted into iron 0. Iron 0. For this step, we have a E naught value, that is minus 0.44 volt. Delta G naught value will be, how many electrons are involved in this reaction? 2 electron, minus 2 into F into minus of 0.44 volt, which is equal to plus 0.88 Faraday's constant. The fourth step, which is non-adjacent species, if you calculate the delta G naught value for this reaction, Fe plus 3, which is getting converted into Fe0, for this step, E naught value is minus 0.057 volt. Delta G naught value will be equal to, how many electrons are involved in this reactions? 3 electrons, minus 3 into F into minus of 0.057 volt. After calculating this, you will get plus 0.171 Faraday's into Faraday's constant. This is how, by seeing this delta G naught values, we can find out the feasibility or stability of the species. From the thermodynamics, for the feasibility of the reaction, delta G naught must be negative. So, Here we can observe there are two negative values. That means these are spontaneous process. These are the spontaneous off reactions. That means Fe plus 3 and Fe plus 6 is unstable, thermodynamically unstable. Understood? Here we have delta G naught values of positive values. That means these are non-spontaneous reactions. That means Fe plus 2 and plus 3 in this reaction is stable. Understood? Calculate the E naught values for non-adjacent species. E naught value for this conversion is unknown. How do we calculate redox potentials? Let's see. Don't know. We are assuming that for the conversion of Fe plus 3 to Fe0 is unknown. E naught value, standard reduction potential value for this step is unknown. But we know that we have a off reactions which converts Fe plus 3 to Fe plus 2, whose E naught value is how much? 0.77 volt, and Fe plus 2 to Fe0 E naught value for this reaction is minus 0.44 volt. This is plus value. Let's see. Now we will construct it again. Fe plus 3 is the highest oxidation among these off reactions. And the next one is Fe plus 2. And the next one is Fe0, which is at solid state. And for this conversion, we have a E naught value that is plus 0.77 volt. And for this reaction, minus 0.44 volt. We have to find out the reduction potential for this reaction. This is question mark. To find out this, we can calculate the E naught values for non-adjacent species by doing sum of delta G naught values for the in between of reactions. Is this one, first reaction and the second reaction. We have to do the sum of delta G naught values for the first reaction and second reaction. That will be equated to the third overall non-adjacent species. So delta G naught value of the overall reaction can be written as delta G naught of 3. Delta G naught value for the first reaction can be written as by using thermodynamic reaction minus NF E naught for the first reaction, and for the second reaction minus NF into E naught for the second reaction. The third reaction can be written as minus NF E naught for the third reaction. Here, N indicates the number of electrons involved in the corresponding of reactions. So, for the third reaction, for this reaction Fe plus 3 to Fe0, how many electrons are involved? 3 electrons. That's why minus 3 into F into E naught value of third reaction we need to calculate, that is non-adjacent species, which is equal to the how many electrons are involved in the first reaction Fe plus 3 to Fe plus 2, that is only 1 electron is involved in the first reaction. What is the value of E naught? E naught 1 plus 0.77 volt plus how many electrons are involved in the second reaction? Here in this reaction Fe plus 2 to 0, there will be involvement of 2 electron, minus 2 into F into what is the value of E naught? Minus 0.44 volt. After simplifying these equations, minus 3F E naught of 3 will be equal to minus 0.77 F minus into minus plus plus into plus plus. So 2 into 0.44, that is 0.88 F. On simplification, to simplify, you need to calculate the E naught value for the non-adjacent species. This value is this one. To do this, you will get 0.11 F divided by minus 3 F. In doing this, you will get 0.5 minus 0.057 volt. That is the E naught value of the third step. Understood? Like this, you can calculate the value of E naught and you can identify the spontaneity of the non-adjacent of reactions. Here, E naught value is negative, means the delta G naught value will be positive, because as we have known this equation, delta G naught value is equal to minus NF E naught. So negative value has to come, means it has to be positive. Here we are getting negative value, that's why this is positive value. That means this is non-spontaneous. Fe plus 3 to Fe0 is non-spontaneous, means Fe plus 3 is stable. And one more thing you need to observe, Fe plus 2 is oxidized to Fe plus 3 ion, and Fe plus 2 ion is reduced to Fe plus 2. That means it is an example for disproportion reaction. Here in this case, you can observe which is whether the oxidation process is spontaneous or reduction process is non-spontaneous, which is action. Here for this step, Fe plus 2 to Fe plus 3, here in this case we have a E naught value is positive. That means Fe plus 2 to Fe plus 3 is spontaneous, and Fe plus 2 to Fe0 is non-spontaneous because the negative value of E naught. This you can study the disproportion reactions and spontaneity, thermodynamic stability, and we can identify the good oxidizing agent and reducing agent. We'll write the Latimer diagram for copper. Here I have a off reactions. That first off reaction is copper plus 2 is accepting 1 electron and to get converted into copper plus. For this, standard reduction potential value is plus 0.15 volt. The second one is copper plus 1 is getting converted into copper by accepting 1 electron. E naught value for this reaction is plus 0.50 volt. These are the two of reaction. Now we will write the Latimer diagram for this reaction, which is the highest oxidation state, copper plus 2, and the next one is copper plus, and the next one is copper 0. We have to connect these oxidation states of a copper species, these chemical species, by an horizontal row. Above this, we need to write the corresponding E naught value. The corresponding E naught value for this reaction is, for the conversion of copper plus 2 to copper 1, is plus 0.15 volt, and for the conversion of copper plus 2 copper 0 is 0. Plus 0.50 volt. Here you can observe one thing, highest oxidation is kept at the left side and lowest is kept at the right side, and electrons are omitted. Electrons which are involved in these reactions are omitted. If you want to calculate the redox potential for the process, that is copper plus 2 to copper 0, you can calculate in the similar way. Here you can observe one more thing, that is copper plus 1 is getting oxidized to copper plus 2, and copper plus 1 is reduced to copper 0. This is copper plus 1 is undergoing both reduction and oxidation together, which is the fastest step or which is the feasible step actions. And we need to find out the delta G naught value for the non-adjacent species. That means copper plus 2, for the conversion of copper plus 2 to copper 0, we need to calculate the value of E naught. Now we need to calculate the delta G naught value for this first step, that is minus N of E naught. How many electrons are involved in the first step? Only one electron, minus 1 into F into E naught value is plus 0.15 volt, which is equal to minus 0.15 volt. Delta G naught value for the second step is minus N of E naught. How many electrons are involved? Here also only one electron is involved in the reaction. That's why we can be written like this. So minus 0.50 F. Now we need to calculate the delta G naught value for non-adjacent species. Which can be written as delta G naught 1 plus delta G naught 2. We have calculated the value of delta G naught 1 is F minus 0.50 F. Here we have a minus N of E naught value for the third step, that is non-adjacent species. How many electrons are involved in this overall process? 2 electrons are involved. That means minus 2 into F into E naught of 3 will be equal to minus 0.65 F. Then E naught value for this conversion is minus 0.65 F divided by minus 2F. So after simplifying these equations, you will get 0.35 volt. That is in the positive value. Here this if the E naught value is positive, the delta G naught value for the third reaction must be negative. That means which is here E naught values you can observe here. This is also a positive value, this is also positive value, and we got the same positive value. Which is the highest positive value of E naught? That is 0.50. That means copper plus 1 is a good oxidizing agent. Understood? Copper plus 2 is comparatively stable because it has lesser value of E naught, comparatively lesser value of E naught. That's why copper plus 2 is thermodynamically stable. Here, for this, you will be having two of reactions. That is, nickel plus 2 is getting converted into nickel plus 1 by accepting one electron. Let us calculate the E naught value for the first step. And the second of reaction is nickel plus 1 is getting converted into nickel 0 by accepting one more electron. For this step, E naught value is equal to minus 1.34 volt. And one more of reaction, that is nickel plus 2 can accept 2 electrons and get converted into nickel 0, that is solid state. For this we have E naught value plus 0.98 volt. By using these off reactions, we'll construct a Latimer diagram. Which is the highest oxidation state? Nickel plus 2. The next one is nickel plus 1 and the next one is nickel 0. We have to connect these species by an arrow. For the conversion of nickel plus 2 to nickel plus 1, the E naught value is unknown. We need to calculate. And nickel plus 1 to 0 conversion is, you can see here, minus 1.34 volt. And for the conversion of nickel plus 2 to nickel 0 is plus 0.98 volt. By using these values, we can calculate the E naught value for the first step. We know that the standard change in Gibbs free energy is additive. That's why delta overall reaction is delta G naught 3 will be equal to delta G naught 1 plus delta G naught 2. Now we will calculate all these things. Now we will calculate the delta G naught value for the third step, that is minus N F E naught, which is equal to, here you can see nickel plus 2 to nickel 0. How many electrons are involved? 2. Minus 2 into F into, what is the E naught value? Plus 0.98 volt. After simplification, you will get minus 1.6 F. And delta G naught of 2 is, how many electrons are involved in the plus 1 to 0? So only one electron, minus 1 into F into E naught value is 1.34 volt, which is equal to plus 1.34 F. Now we need to calculate the delta G naught value for the first step. So delta G naught value for the first step is, how many electrons are involved in the first step? That is here nickel plus 2 to plus 1, only one electron F, and E naught value of the first step is unknown. To calculate this delta by using this equation, delta G naught of first reaction will be equal to delta G naught of 3 minus delta G naught of the second of reaction. So delta G naught value for the third reaction is minus 1.96 F, and for the second step is plus value, plus into minus, minus 1.34 F. By adding this, what do you get? And you get minus 3.3 F. Is it not? After calculating this, you will get E naught value for this step is, for the first step is minus 3.3 F. Here you have to write F. F will get cancelled on both sides. E naught for the first step is plus 3.3 volt. So you can observe this is the highly positive standard reduction potential. That's why nickel plus 2 is a good oxidizing agent. It's proportion reaction also. Nickel plus 1 is oxidized to nickel plus 2 and reduced to nickel 0. This is also an example for disproportion reaction. I'm going to write the Latimer diagram directly. Cobalt oxide, which is get converted into cobalt plus 3 and cobalt plus 2 then, and again cobalt 0. So here the cobalt is in the plus 4 oxidation state, which is the highest oxidation state, and this is the lowest oxidation state. We have omitted the number of electrons which are involved in this of reactions. For the conversion of cobalt plus 4 to plus 3, the E naught value is plus 1.4 volt. Similarly, for this of reaction is plus 1.92 volt, and the third step is minus 0.282 volt. Now you can calculate the E naught value for non-adjacent species, like from cobalt 4 to cobalt 2 can be find out. You can find out for this of reaction also. For this non-adjacent species also, we need to calculate the E naught value for this reaction, the standard reduction potential. For this overall reaction, delta G naught will be equal to the sum of delta G naught value for the first step and the second step and for the third step. After doing the addition of 3 steps, you will get the value of delta G naught value for the overall reaction. Now we will calculate one by one. Delta G naught value for the first reaction is minus NF E naught. That means minus how many electrons are involved in the first step? Here in this step, only one electron is involved in this reaction, into F into what is the E naught value? That is plus 1.4 volt, which is equal to minus 1.4 volt. Similarly, for the delta G naught, 2 will be equal to how many electrons are involved here in the second step? Only one electron, 1 into F into E naught value is plus 1.92 volt, which is equal to minus 1.92 F. And delta G naught 3 will be equal to, here you can observe cobalt 2 to 0. There are 2 electrons are involved, minus 2 into F into E naught value is minus 0.28 volt, which is equal to 0.56 F. If you get the summation of these values, delta G naught value for the overall reaction is the summation. So that means minus 1.4 F minus 1.92 F plus 0.56 F is minus 2.76 F is the delta G naught value, which is negative. And by using this data, you can calculate the value of E naught. That is, E naught for the overall reaction is equal to delta G naught value for the overall reaction divided by minus N into F, where number of electrons involved in the overall reaction. That means cobalt plus 4 to 0. Here there are 4 electrons are involved. We know that the delta G naught value for the overall reaction is minus 2.76 F divided by 4 electrons involved into F. If you simplify this, 0.69 volt. So this is the E naught value for the overall reaction. The similar way, you can find out the value for the non-adjacent species. Like, we'll calculate the delta G naught value for this step. That means cobalt plus 3 to cobalt 0. So here, the delta G naught for this conversion is, let it be delta G naught value for first reaction I have mentioned as 1 amplification, which will be equal to this. Let me call this as A reaction, will be equal to delta G naught value for the second and delta G naught value for the third, which will be equal to, you have to consider these two values only, minus 1.92 F plus 0.56 F. You will get minus 1.36 F. How many electrons are involved in this reaction? 3 electrons. That's why minus 3 into F into E naught. So delta G naught value is this one for the conversion of cobalt plus 3 to cobalt 0. To find out the E naught value for the A reaction, E naught of A reaction is equal to minus 1.36 F divided by 3, minus 3F, which is equal to plus 0.45 volt for this conversion. Similarly, you can calculate the delta G naught value for the conversion of cobalt plus 2 to cobalt plus 2. Here there are the overall number of electrons is plus 4 to plus 2. That means 2 electrons are involved in this reaction. You can calculate by using this. By identifying E naught value and G naught value of these reactions, you will get thermodynamic stability information of the reaction. Like this, you can construct many Latimer diagrams. In your syllabus, another two Latimer diagrams are prescribed, that is manganese and for chromium. I'll write the Latimer diagram directly. First, we will write the Latimer diagram for manganese. Here, we have a Mn4 ion, MnO4 minus ion, that is manganese ion, which is get converted into MnO4 minus 2, again MnO2 manganese dioxide, Mn plus 3, Mn plus 2 oxidation state. Finally, it gets converted into, which is 0 state, that is the lowest oxidation state. Here, the manganese is in the plus 7 oxidation state. You can calculate plus 7 oxidation state, which is the highest oxidation state, and 0 is the lowest. We have neglected electrons, H plus, the acidic or basic medium, H plus ions, OH minus ions, we have neglected. Here MnO4 minus 2, the Mn will be in the plus 6 oxidation state, and which is in plus 4 oxidation state, and this is plus 3, plus 2 and 0. This is in the decreasing order of the oxidation number. The electrode potential for this conversion is 0.56 volt plus 0.56 volt. Similarly, for this reaction is plus 2.26 volt. Similarly, for this 0.45 volt for plus 4 to plus 3. Plus 3 to plus 2 oxidation convert for the off reaction, plus 3 to plus 2 oxidation is plus 1.51 volt. For the conversion of Mn plus 2 0, the redox potential value is minus 1.19 volt. And for the overall reaction, that means MnO4 minus 2, that is, which is in the plus 7 oxidation state to 0 oxidation state. Here there are 7 electrons are involved, plus 7 electrons are involved in this reaction. For this, E naught value will be equal to plus 1.51 volt. Here you may have different non-adjacent species. MnO4 can get converted into MnO2. Is it not? This is one non-adjacent species. Here the number of electrons involved is 3 electrons involved in this step. For this, E naught value is plus 1.69 volt after calculating. In the similar way, Mn plus 2 can get converted into Mn plus 2. For this, the number of electrons involved, plus 4 is the oxidation state, here plus 2, there are 2 electrons are involved in this reaction. For this, E naught value is plus 1.23 volt. And you can calculate many non-adjacent species. Calculate the E delta G naught value for the conversion of Mn, which is in the 6 oxidation state, to Mn plus 3 oxidation state. Okay. Similarly, you can calculate the delta G naught values for delta G naught and E naught values for many non-adjacent species like Mn plus T, conversion of Mn plus T to Mn0 oxidation state. Both in this case, 3 electrons are involved. N is equal to 3. And the next Latimer diagram is for chromium. Chromium, the highest oxidation state of chromium is 6x, which can get converted into chromium 5 and then chromium 4 plus 4 oxidation state and plus 4 oxidation state to chromium 3. Chromium 3 can convert into chromium 2 and finally it can convert into chromium 0. Here for these conversion E naught values for these conversion is plus 0.55 volt plus 1.34 volt plus 2.1 volt minus 0.424 minus 0.90 volt. And you can calculate the value of delta G naught and E naught value for the conversion of chromium 6 to chromium 0 by using this equation. You have to calculate this. This is a homework problem for you. And the calculated non-adjacent species E naught values are chromium 6 to 4. Here you will be having plus 0.95 volt. Similarly from 5 to 3, the E naught value is 1.72 volt. Similarly 6 to 3 is 1.38 volt. In similar way, plus 3 to 0 oxidation state will be minus 0.74 volt. This is the Latimer diagram for chromium. In this way, you can construct a Latimer diagram for the elements which exhibit multi-oxidation states. This Latimer diagram is only for the elements which exhibit various oxidation states, more than one oxidation states. You can get the information about, as I said before, the feasibility, thermodynamic stability, oxidizing and reducing property of chemical species, and disproportion reactions can be studied by using this Latimer diagram. With this, thank you.